Okay, so for this last video for this lecture, we're going to be talking about different components to muscle recruitment and summation, as well as some length-tension relationships. So from a physiological perspective, there's only two ways that we can increase the amount of force a skeletal muscle can generate. One is summation, and two is recruitment. So with regards to recruitment, this references our ability to activate more motor units, right? So for example, our bicep muscle is made up of many motor units and are all interlaced together. If we want to perform a 1 rep max, we need to recruit all available motor units that we could possibly use. Then we need to summate them. So recruitment comes first, right? So the more motor units we can recruit, the larger amount of force we're going to be generating, right? Because each motor unit has an alpha motor neuron, remember, and all of the muscle fibers it innervates. The more of these units, motor units we recruit, the more muscle force we're going to get out of one large muscle. Okay, so when we talk about summation is we need to increase the rate at which each motor unit was firing. So if you increase the rate, you're increasing the amount of calcium in the cytosol. By doing so, you will then increase the force being generated. So you need to do both. You need to recruit more motor units, and then you need to summate them together to generate the greatest amount of force possible. So again, summation is we need to increase the rate at which each motor unit was firing. If we increase the rate at which the motor unit was firing, we're going to increase the also calcium content within the cytosol, which is going to increase the amount of force we can generate. So calcium is a huge player in the amount of force as well, due to its relation to summation. Okay, so when we're talking about recruitment and summation, again, recruitment is where activating more motor units. Summation is where we're increasing the rate at which each of those motor units is firing. So when we look down here at these diagrams, with regards to summation, this is a right here. This is ultimately representing the motor unit firing, and the more we recruit and the faster we fire, the larger the amount of force it's going to be due to the increased amount of calcium content within the cell as well. This diagram's referencing incomplete tetanus, and then tetanus over here, where we're just doing one complete contraction and there's no little waves and there's no more firing. It's just one constant firing. So with tetanus, if you increase the rate at which the stimulus is arriving so that you don't allow for any recovery, you will have a tetanic contraction. So now you have smoothed out the hump some and are generating force in proportion to the calcium being released. The ability to generate a tetanic contraction is determined by two factors. One, the muscle's ability to tolerate the increase in calcium concentration within the cytosol. So if the muscle can deal with it, then we'll get a nice smooth contraction that will give us a really good amount of force. Two, the muscle action potential cannot last as long as the twitch contraction. Ultimately, this means that the action potential has to be shorter than the mechanical response itself. So when we talk about a tetanic contraction and a muscle twitch, there's 4 components, A, B, C, Ds, like what you see right here, which requires we need that stimulus, so we need that electrical signal. But then we actually have what's called a latent period, and then we actually contract the muscle, and then we relax the muscle, right? And then we keep doing that, and then we summate. The faster we fire that motor unit, the more calcium comes in, the higher amount of force we get. And again, this is incomplete tetanus. Again, we're firing that motor unit many more times, and then we get a nice smooth muscular contraction once that our cytosol can handle the amount of calcium that's being put in it. So what is the latent period, right? So we're going to have a stimulus in order for us to contract, right? So we have that action potential coming down to act as that stimulus right there, which is A. What is this latent period right here? It's the time between the actual stimulation of the contraction and the actual movement of the resistance. So there is actually a time factor here. So we're actually going to be stimulated to contract But again, there's going to be a time lag in order for us before we actually do contract, right? So we just went over all of those components of the acetylcholine's got to come down and do this and release all the calcium and bind and do all these other things. So there is a latent period there before we actually contract that muscle from when the stimulus occurs to actual muscular contraction or movement of that resistance. Okay, so now we're going to briefly talk about the mechanics to muscular contraction. So if we were to take out a muscle out of its attachments and place it right here on the table, right in front of you. If you were to take a muscle off of its attachments, just take one full muscle, put it right on the table. It would form to its equilibrium length, correct? Right? So at some point, once you place it on the table, it's going to come to some sort of equilibrium length where it likes to just lay normal if we were to disattach it from its attachment places. So if we were to stimulate that muscle right then and there at its equilibrium length, that muscle would give us X amount of force just at its equilibrium length. Now we can do this, we can do a series of manipulations to this muscle that's sitting right here on this table to see if we can alter the force that that muscle gives. So let's talk about stretching first. If we were to stretch that muscle a certain percentage above resting length and now then stimulate it again, we will be able to generate more force than when it was at its equilibrium length. So ultimately now we have X plus Y equals Z, which is our new force, which is our new total force. So we have a resting force plus our new force, which equals now our total force. So if we stretch this muscle fiber, it's going to give us a greater amount of force than if we were just to stimulate it at its equilibrium length. However, if we continue to stretch the muscle fiber beyond a critical point, the amount of force you can generate will go down. Why is that? That is because now you're disengaging those cross bridges, so those actin and myosin. If we stretch the muscle fiber, we will get a greater amount of force to a given extent. But if you stretch it too far, what will occur is you're going to disengage those actin-myosin cross-bridge cycling. They won't be able to attach to each other. So actually your force is going to go way down because you can't even generate force at that point. So if you stretch it within limits, you can generate a larger force. However, if you stretch it too much, you can actually this is where you're going to have muscle tearing or damage, and you will not be able to generate force. So to a certain extent, you can stretch it and get a greater amount of force. Now, if we take the same muscle from equilibrium length, let's go the opposite way. We're going to shorten it some. So let's picture that muscle sitting right there, and we're going to squish it together. We will have actin bands bumping into each other and overlapping. There will be some confusion of where those cross bridges are. They don't know where those active sites are. So now we have muscular interference, and the amount of force will go down. There's no exact number that determines how much stretch is appropriate. It can vary from day to day and from person to person and, how flexible someone is and all of that. Some say between 6 and 8%, and some say between 12 and 15%. So it seems to be kind of a large range. So if we say anywhere between stretching a muscle from 6 to 15%, we may be able to get a greater amount of force. This is the principle that is the essence of plyometric training. We stretch, contract, and so forth. And that's pretty much the essence of what plyometric training is. Okay, so what I just described to you was the length-tension relationship. So I want you to look at this diagram right here. And again, we want to take a muscle, and if we put it on the table or put it at its equilibrium length and stimulate it, it's going to give us X amount of force. Now, if we stretch it to a certain extent, again, maybe possibly between 6 and 15%, depending on the person, we can actually get more force from that those stretched myofibers. Now, if we were to do the opposite, and we're going to decrease it, and we're kind of squish the muscle together, we are going to have some overlapping, right? Some actin bands are going to bump into each other, and the myosin may not be able to find their actin active sites. So ultimately, that force is going to go down as well. But again, if we stretch it too much, we're going to disengage completely those cross bridges, and we're not going to have any sort of force. So this is kind of what that's showing right here, right? So if we decrease the length, we're going to have minimal force. So if we squish this muscle together, we're not going to get as much force as we possibly could. Then if we kind of go a little bit more so up to equilibrium length, we are going to get X amount of force as well. However, if we start to stretch it a little bit, we can actually get an increased amount of force up here. All right, so if we stretch it, if we lengthen a bit, we can get a larger amount of force. However, if we stretch it too much, what's going to happen? We stretch those myofibrils too much, boom, we're going to disengage those cross bridges, actin myosin can't even bind on to each other, and boom, we're going to decrease the amount of force. So this length-tension relationship ultimately is stating that if we stretch the muscle to a certain extent, we'll be able to generate a larger amount of force, and we'll be able to move a heavier load. If we shorten the muscle, shorter than its equilibrium length, we're going to have some confusion within the muscle fiber itself with those cross bridges. So once we stimulate it, we're not going to get as much of a force as we could at equilibrium or a stretched length. And then lastly, if we stretch the muscle fibers too much, we may disengage those cross bridge cycling where they don't even interact with each other, and we're going to have a large decrease in force. Okay, that is it for lecture 5 for neuromuscular physiology. I know we did just go over a lot of material, so hopefully we'll get to review some of it in class. And if you have any questions, just shoot me an email. All right, thanks everyone.